Let's discuss how quadratic equations can be used to solve differential equations. Differential equations can describe exponential decay or oscillations with or without damping. I have made a dynamic picture. Let's take a look on that. Here the parameters are in such a way that the differential equation describes an exponential decay. If I change the parameters, the equation will describe an oscillation. We can see a mass bouncing here, and as time goes by, the oscillation gets smaller and smaller. In the end of this lecture, you will be able to understand this, but let's first look at the formulas. A quadratic equation like this has these solutions. Depending on the discriminant d, we will have two real solutions, one real solution, or two complex solutions. In this case, the discriminant is positive and we have two real solutions. Here the discriminant is 0 and we have just one real solution. And in this case, the discriminant is negative and we have two complex solutions. Let's have a couple of examples where we solve a second-degree equation. In this case, all the parameters are divisible by 2, so we can divide them by 2. Then let's take the parameters a, b, and c and substitute them to the formula. After calculations, we will get this. If we choose plus square root of 1, we will get that x is equal to 2. If we choose minus square root of 1, we get that x is equal to 1. It's a good habit to always check the solutions, so let's substitute x equal to 2 to the original equation. After the calculations, we get 0, so it means that x truly is a solution for our equation. And let's also check the other solution. In this equation, we can find a, b, and c and substitute them to the formula. In this case, the discriminant will be 0 and the square root will have no effect. So x will just have one value, 3 by 2. We can check the solution by substitution. In this case, if we calculate the discriminant, it will be negative. To proceed, we need to calculate what is the square root of minus d. In this case, it will be 6. After adding an imaginary unit to our formula, we will get that x is one of these complex numbers. We can check this answer by computer. But do quadratic equations have any real-life applications, and how about these complex solutions? They seem very odd. Many real-life problems have quadratic equations related to those. For example, in area problems, we can here have areas x squared and constant times x. If you throw an object, the path will be a parabola, and it is related to second-degree equations. But let's now talk about differential equations. A differential equation like this looks like our second-degree equation. The second-degree equation is the characteristic equation for this differential equation. If we would have this kind of simple equation, it would describe the radioactive decay of some substance. We write the characteristic equation, which has only one solution. And we will just have one function like this, which has exponential decay. When d goes to infinity, the function will go to 0. If we have a second-degree equation with d equal to 0, again we have just one exponentially decaying solution. If d would be positive, we would get two different values of r. It means two exponential decaying solutions. For example, in Fukushima, there was a nuclear disaster and 2 radioactive substances were released. After T years, the radioactivity follows this formula. We see that iodine decays very fast, but caesium decays slowly. Because of this, to prevent iodine radiation damage, you need to eat iodine tablets, and caesium makes the area inhabitable for many years. Many Finnish people rush to the pharmacy to buy iodine tablets, and now you cannot go to Fukushima. However, if in the characteristic equation D is negative, we will get that R has also an imaginary part. In that case, the solution will have an exponential decay component and an oscillation component with some angular frequency. Let's talk about these oscillations. Without any damping, the oscillation will continue forever. If we add some damping, the oscillation will finally stop. Let's discuss the first case first. In this case, to the object, there is only one force. By using Newton's third law, we get this kind of differential equation. We can solve the characteristic equation, and we see that the solution will always oscillate. If we add a shock absorber, which makes a force related to the speed of the object, the equation will become a little bit different. If this capital R is large, then the discriminant will be positive, and we see that there will be just exponentially decaying solutions. If the discriminant is negative, we will get an exponential term times an oscillating term. Depending on how the R is, the damping can be faster and the angular frequency can change. Let's check this. If R is large, everything will have exponential decay. And if R is small, we have oscillation. We see that when R changes, the decaying becomes faster or slower. And when R grows, also the angular frequency will change. Not very fast, but still it will. When R goes and is large enough, the angular frequency will go to 0, and the oscillation will stop. I will leave this example for you, and you can try how the parameters affect the solution.